Swayam Prabha. Digital India. Educated India.
Welcome to the 7th lecture in this particle characterization course. In the last lecture, we started discussing particle size measurement techniques, and I mentioned that essentially particle measurement strategies can be classified as being in static mode and in dynamic mode. So, we looked at a few examples of size characterization in the dynamic mode, where essentially particle populations are set in motion, and based upon their behavior under the flow field, we derive their particle size distribution characteristics. And then we discussed static methods, and the first thing to realize is that in order to analyze particles in a static mode, you first have to capture them and immobilize them so that they can be inspected, and we discussed various techniques for doing this, including impactors, impingers, and filters, and so on. So, in this class we are going to assume that we have employed one of the methods that we talked about in the last class to fix a particle in its place, and now we want to characterize its size. The most obvious method for doing size analysis in static mode is visual inspection. If a particle is large enough, you can inspect it once you have collected it on a slide or a filter or some medium with just your naked eyes and do a reasonable size assessment. As the particle size gets smaller, you may need to resort to some magnification, the simplest thing being a magnifying lens, which I am sure you have all used, and then an optical microscope, and finally transitioning to an electron microscope as the particle size decreases. Now, I mentioned the other day that the human eye can actually see particles that are as small as 50 microns. However, the resolution of the human eye is only about 200 microns. In other words, it cannot distinguish between two particles that are less than 200 microns apart. So, if you want to improve your resolution to, let us say, half a micron, then obviously you need at least about a 400x magnification, right. And so, optical microscopes were essentially designed to provide magnification in the range from 5x all the way up to 400x originally. Now, more recently technology has improved to an extent where even an optical microscope can give you close to 10,000x magnification. So, you are actually able to see particles even in the nanometer range using simple optical microscopy. Of course, the technique is never going to be as powerful as scanning electron microscopy, primarily because of the method of detection, which still involves essentially geometrical optics, whereas electron microscopy is makes use of a completely different methodology involving bombardment of the target with electrons. So, optical microscopy does have its advantages. For one thing, much cheaper. Secondly, the fact that electron microscopy typically needs to be done under high vacuum. So, you really have to take the sample, put it inside a chamber, and apply very high vacuum in order for you to do electron microscopy, whereas optical is something that you can do in an ambient environment. There are several other pros and cons of optical versus electron microscopy, and we will discuss this in more detail as we go along in this course. But one of the first things I wanted to point out is that there is a formula for calculating the resolution of a microscope, and you're probably familiar with that formula. Resolution is given as 0.5 lambda over gamma sin alpha, where lambda is the wavelength of the optic light. The denominator gamma sin alpha is termed the numerical aperture, and gamma is the refractive index of the medium, and alpha is the angle subtended at the lens. So, in optical microscopy, if you want to improve the resolution, the parameters that you can really control are the wavelength and the refractive index of the medium. Now, most of the time when you do optical microscopy, the particle is going to be essentially sitting on a surface which is surrounded by air, and so the refractive index of the medium also tends to be reasonably fixed. So, the parameter that you do have some control over is the wavelength. So, now you are talking about the visible range. When you talk about optical microscopy, you are only concerned about the Vibgyor range, so to speak. So, if you look at the range for normal visible light, it ranges from about 0.4 to 0.8 microns, right. Lasers, for example, helium neon laser has a wavelength that is sort of in the middle of this wavelength range for visible light. So, again, when you look at this, there is not a lot of room there for manipulation, and so the way that optical microscopes are now improving that resolution is really by playing around with the optics more than anything else. There is not a whole lot you can gain by trying to play with these parameters. Now, optical microscopy, as I mentioned, typically today is okay till about half a micron in most conventional microscopes, but there are what are known as high resolution or high res microscopes which can take this down to roughly 0.05 microns. Because as the resolution increases, there is a penalty that you pay, and that is the fact that you are able to scan only smaller and smaller regions of the surface. The penalty that you always pay for higher magnification, higher resolution, higher sensitivity is the fact that the sample under consideration shrinks in size. So, for example, if I want to look at particles on this surface, if I were to use naked eye inspection, I can look at the whole surface within 10 seconds, right. If I use a magnifying glass, you can imagine that for me to go over this entire surface may take about an hour. If I start using an optical microscope, it's going to take me, I don't know, maybe a day to analyze this entire table. If I start using an electron microscope, for me to just analyze this surface can take up to a year, right. So, that gives you some idea about the scale of times that we are talking about. Now, when we do again optical microscopy, there are essentially two ways in which microscopy can be done, and that has to do with lighting. I mentioned that resolution is now being improved by looking at other factors that influence the operation of the instrument, and light is certainly one of them. The same surface, if I were to inspect it under, let us say, normal lighting versus suppose I had high intensity lighting, focus lighting, or even oblique angle lighting, would show up particles very differently. And so one of the tricks that are used that in optical microscopy is that conventionally in what is known as bright field microscopy, you illuminate the entire surface with bright light, and defects and particles on the surface will then show up as dark spots. Now that technique works well for the most part if there is a clear delineation between a surface defect and a surface particle. Now in many applications you may not care, but sometimes you do. You want to know whether something that you see on the surface is actually a feature of the surface or whether it's actually something sticking on the surface. Now to be able to resolve between those two can actually be quite difficult, and dark field microscopy was actually introduced essentially to address this issue. So in dark field microscopy, the surface that you are looking at will essentially be dark, and the surface features will then shine in contrast. When you do that, you can actually fairly effectively distinguish between surface features or defects and surface adhered particles. So dark field microscopy provides you with the ability to resolve surface features with better clarity than bright field microscopy. Now the way this is done is in bright field microscopy you are essentially using the same aperture to capture both the reflected light as well as the scattered light, whereas in dark field microscopy you are essentially only capturing the reflected light, and therefore the contrast that you see between the surface and the particle is quite different in dark field microscopy and bright field microscopy. There is another way in which you can distinguish microscopic techniques. When you have a large flat surface and you are trying to do microscopic analysis of the surface, you can either initially capture an image of the entire surface and then use software to do your scanning. So for example, you would capture this image of this, for example this tabletop in a camera or some kind of a CCD, and then use various algorithms to analyze the image and obtain the information that you are seeking. This is basically called the imaging mode of analysis. The other mode of analysis is what is known as the scanning mode. In the scanning mode you will not try to do image capture, instead it is basically real time analysis of the surface. So you will essentially take your optics and traverse the entire surface with it, and as you do you are constantly getting a signal back to the instrument and you keep track of it. Now here you will use certain devices like photomultipliers in order to intensify the signal that you are getting from the surface, but you are looking at it real time. Now there are obviously advantages and disadvantages to doing that versus doing the image capture methodology. When you do direct scanning, the feedback is immediate and it is a highly sensitive instrument, because you can see real time as you slowly move your scanner across a surface, you will see that the signal that you are seeing back is changing, and you can quickly draw inferences and conclusions based on that. However, you can imagine that, for example, if your surface is very rough, then the interference that you get from the surface is going to be of the same order of magnitude as the particle or defect that you are trying to analyze. So this type of continuous scanning methodology works very well when you have highly polished and smooth surfaces. For example, silicon wafers. The semiconductor industry uses scanning microscopes extensively because most of the time they are dealing with surfaces that do have a high degree of finish, and the surface roughness is of a scale that is much smaller than the particles and other defects that you are trying to characterize on the surface. On the other hand, if I were really trying to characterize particle distribution on this surface, I would not try to do it in a scanning mode, because I will just get too much noise compared to the signal, the noise being the reflection and scattering that you get from the surface itself. Instead, I will try to grab as refined a picture or image of the surface as possible, and then depend on my processing software to eliminate the noise and give me as clean a signal as possible. Now, there are various companies that really specialize in making both dark field and bright field microscopes, imaging and scanning microscopes. One of them is KLA Tencor. You may have heard of them. I think they come and recruit in India quite extensively. They are located in the one of the IT parks on OMR. They are one of the major manufacturers of semiconductor characterizing equipment. Another company that's a leader in this field is Applied Materials. Applied Materials primarily emphasizes analysis of process equipment rather than product wafers. There are other companies that operate more in niche markets. There's a company called Candela Instruments who specialize in scanning of magnetic disks that are used in hard drives to look for contamination and defects. There is another company called ADE who primarily focus on the silicon wafer inspection market. So there's another company called Inspex, which is also a player in the silicon area. So there is some market segmentation of these various companies, but they all do one of these four. They either do image analysis or scanning analysis, and they all do either bright field or dark field analysis. Now, most of these techniques are useful for looking at surface particles. Now, either the particles may be on the surface inadvertently,